The mini-sum multi-facility location problem involves a situation where you have more than one new facility, but instead of being just solving multiple single facility location problems at once, what makes it a multi-facility location problem is that there are flows and interactions between the new facilities. So as a result, the location, since all of the new facilities are going to be located together, the location of them has to be determined as an integrated solution procedure. They cannot be done in separate form, as would be the case if they were just a series of multiple single facility location problems. So the first example we're going to look at is a simple single facility location problem where we have 3 existing facilities and weights 4, 3, and 5. We can calculate our total cost handle and then use fmin search as a way of solving that single facility location problem, or we could use MATLAB's mini-sum location procedure. In either case, we get the same result. To turn this into a multi-facility location problem, we can basically take the W vector before and then add a second row to the vector. So this is the original row, and now we're going to add a second row, and that second row then represents the interactions of the second new facility that we'll be locating with the 3 existing facilities. And then the other thing we need to do is add a matrix that we'll call V, and that represents the interactions between the new facilities. So in this case, this is a 2 by 2 matrix, and it has a value of 1 in the first row, second column. So that means there's essentially a flow of material from new facility 1 to new facility 2, in addition to the interactions between new facilities 1 and 2 and the 3 existing facilities. So I can go and create those 2 matrices, and then I can modify my total cost function handle by adding the addition of the sum of the V elements times the distance from the new facilities to each other. And here the distances I'm using in this example are all Euclidean distances. So this defines my function handle, and then I can again use either fmin search, or here when I use mini-sum location, I've added a 4th input argument, and then it automatically solves it as a multi-facility location problem. If I had 2 rows in my W matrix and either I left the V matrix out or gave a default value of an empty matrix, then mini-sum location would solve 2 single facility location problems using each row of W as the weights for each single facility location problem. So we get this as the combined multi-facility location problem. So here I'm going to do that and solve it as 2 single facility location problems, setting V equal to the empty matrix. And then I can solve it. I'm going to assign it to 2 different total cost values. Total cost 1 and then total cost 2. Add those together, get a value of 18.09. And I can compare that to the previous 19.43. The additional cost for the multi-facility is because of the cost associated with the interactions between the new facilities. Here I can solve it, and here by not specifying the V matrix, it just gives me 2 single facility problems. Right. So that's the basic multi-facility location problem. It's something that it doesn't, at least in my practice, has not occurred very often, where I've had to actually locate multiple new facilities that interact with each other. Most of the time we're dealing with distribution centers that don't typically transmit significant material between each other. It's between suppliers and the distribution centers, and then the distribution centers and the customers. That situation can be captured by the facility location-allocation problem, and that is essentially solving multiple single facility location problems. But here What's different about the location allocation problem, even though we're dealing with multiple facilities, what's different about it is that in the prior case with multi-facility location problem, once we've defined our W matrix, it basically stays fixed, and then we're just solving for the locations of multiple new facilities. What's different about the facility location allocation problem is that in addition to solving the location problem, we're also determining what is the best allocation of existing facilities to new facilities. Implicitly, that means that all of the existing facilities don't have to be assigned or interact with all of the new facilities. They just have to be associated typically just with one. And in most cases, it's the one that's closest to the new facility. The only case where it would not be assigned to the closest typically is situations where the facility or distribution center that it would be closest to is at capacity and does not have room for the material from the existing facility. In that case, you would maybe look at finding the second closest facility. But as long as we don't have any capacity constraints, then it would typically be the closest facility. So for this problem, what I'm going to start with is a one-dimensional problem, and I'm going to use the cities along I-40 that we've talked about previously, the 7 cities. So I'm going to define my P matrix to be just the mile markers of those 7 cities, starting in Asheville all the way to Wilmington. The number of existing facilities is equal to 7. And for this example, I'm just going to set the monetary weights equal to 1 through 7, just to generate different values. And then for this problem, I'm going to set X as my starting point, and I want to solve a problem where I'm locating 2 new facilities, and I want to allocate the new facilities to the closest existing facilities and use that as my way of performing the allocation step. So here I have X, and these are the mile markers. So I'm going to start my location problem with the first new facility at mile marker 100 and the second at 300. And then I'm going to N is equal to 2. That's the number of new facilities. P, I'm going to be using rectilinear distance. Again, for one dimension, it doesn't really matter. This would also work if P was equal to 2 for Euclidean distance. So the first step then is I want to calculate the distances, which is a 2 by 7 matrix. And then in terms of doing the assignment, if I do argmin, calculate A, that gives me a way of allocating the distances to the 2 new facilities based on which is closest. So when I do that, I can see in terms of the weights, the first 3 cities are assigned to the first, and then the remaining 4 cities are assigned to the second new facility. And for that, I can calculate the total cost of $17.60. For this problem then, that's basically using a fixed set of locations for the new facility. I can make the total cost a function of the location X. So given the location X, I can do what I essentially did in this previous cell and combine it all into a single function handle. So I'm nesting one thing after another, starting with the distance calculation, and then using that, applying the argmin function to get this first argument, and then expanding all of this to essentially get my W value, which I have here, and then here is my distance matrix. So this, instead of individually performing each step, assigning to a variable, I can do it all as one function handle. The problem with this approach is, in terms of when you do this, it's hard for anybody to look at what you're doing and really understand what you're actually trying to calculate. So it's probably a good idea to indicate in terms of your labeling exactly what you're doing. And it wouldn't be maybe a bad idea to actually maybe comment and indicate these steps are what actually are occurring within the function handle. So beware when you do so much nesting of commands, it really makes it hard for somebody to decode. But the reason we're doing it is that we can put it all into one function handle. And that's sort of the advantage we get from that. So I'm going to go ahead and create that function handle. And now when I evaluate it at those 2 points, I get the same 1760. For the problem, one of the reasons we used a one-dimensional problem is that for a one-dimensional problem, when we're looking at locating 2 new facilities, then we can essentially turn that problem into a 3-dimensional problem where the first 2 dimensions are the location of the first and second facility, so that's sort of the X and Y coordinates. And then the Z direction represents the total cost given the two new facilities at those particular mile markers. So I'm going to go ahead and just execute this entire command, and you can see the surface plotted here. It turns out it's symmetric. So if you look at this figure and look along the diagonal, we essentially have the same contour plot on either side of the diagonal. So we can essentially ignore either half of this and focus just, for this example, I'm going to just focus on the bottom half. And what this is saying is that for this particular problem, unlike the single facility location problem, where we essentially had a bowl and it didn't matter where we started, we got to the bottom of the bowl. This is a problem, a nonlinear optimization problem that doesn't always get us to the same solution. And this is a little bit different scenario than we dealt with earlier in the homework and in the situation where we had a region. And essentially in that case, we were adding constraints. And as a result of that, that constraint blocked off the single optimal solution and gave us optimal constrained solutions that were along the perimeter of that region, that restricted region. Well, that's one example of a case where we don't have a single optimal solution. Our solution we got actually depended on where we started. In some sense, this is a similar kind of thing, but it's different in the sense that this problem really has no constraints. And even just the objective function alone, when we look at it, actually has multiple solutions. So this is sort of so in some sense, the previous problem, the additional constraints kind of made it into a multi-optimal problem. But this one is fundamentally a problem that has multiple local minima. So it's fundamentally a more difficult problem to solve. So when we solve it, depending on where we pick our starting point, we're going to typically end up in either of these two minimum locations. So we have two solutions, and one of them is the better or global minima that has the lower total cost. But we can't determine that easily. It basically takes more computation to actually do that. So one first way of doing it is to take the problem and look at an integrated formulation where we're essentially using the function handle that we created before, and all we need to supply to it is the X location. So we can call fmin search and just keep changing the X location. And when that is done, there's enough there to actually calculate the total cost. So with this approach, I'm going to set the seed here so you can duplicate this result. Here I'm going to use a function called randx. And what randx does is it generates n random starting points within a bounding rectangle that is occupied by P. We could probably do better than a bounding rectangle by using the convex hull, but it's more difficult to calculate. So not much more difficult, but a little bit more difficult to calculate. So we're just going to take a bounding rectangle that encloses all of the points P, and then randomly pick a point within that rectangle and do it n times for the n different starting points. So with that random starting point, again, I'm just going to go ahead and execute all of this, and then we can call fmin search, and we end up with this result, and we end up with this solution. And looking back at the figure, first let's notice the points 420 and 269. So going back to the figure, basically it corresponds to this point here. 420 is our first coordinate, and then 269 is the coordinate along the x2 dimension. I labeled these x1 and x2 instead of xy, just because these are really just two one-dimensional points. And we're kind of using this to kind of just be able to visualize what the actual problem is. So we basically have a solution point right here with a total cost of 1.05 to the third power. We can run it again, and this will, and here I'm calling it, and I'm using the randx function, so I have a different starting point. And when I do that, I can see here, actually here I've plotted in the upper coordinate. And for this solution, we actually have this point as the solution found. The second approach is to use an alternating formulation. And this alternating formulation is first, for a given set of starting locations, is first going to do the allocation procedure. And then for that allocation, solve a series of location problems. and then from the new locations, resolve the allocation procedure, and basically keep doing that until there's no further decrease in the total cost. At that point, the procedure stops and takes that as the local minima procedure. That's the ALA, we'll call the ALA procedure, alternate location allocation procedure. So with the second approach, I'm going to first calculate a total cost. And for that total cost, it's going to have two parameters. I can pass it both my matrix W, that's going to represent my allocation, and my current location. And from that, I calculate what is the total cost of that. And then I'm going to separate my allocation and location into two separate function handles. The first one, to do the allocation, well, basically I can do the allocation as long as I have the location, the current location of the new facilities. So with that, I'm able to plug in, and notice here I'm using that X to calculate my W matrix, and that then is what is returned from the allocation procedure. The location handle takes the matrix W as an input, and then also it takes, in the case of solving the location problem, it takes a starting location for the F min search procedure. So it can't work with just W by itself. Otherwise, we'd have to pick a random starting point every time we locate it. So if we want to use our current location, which is probably going to be closer to the optimal, it's a good idea to add the second input argument of what our current location is, and then use that to get the new location, which is what is returned from the F min search procedure. And then I'm going to set the seed, go ahead and execute all of that. And then I can do one run of the location allocation procedure. And I'm basically just using this while not done loop. And then within the while not done loop, I'm testing to see whether or not my current cost is still less than my best found cost so far. And if it is, then it becomes the new best cost. If not, the else condition is I'm finished. So done is set equal to true, and this while loop exits with this result. And then I'm going to be also using the fprintf command so I can see all of the intermediate total costs that are evaluated by this procedure. So when I do that, I can see that very quickly it printed. These are the three different total costs. This is the initial based on my starting point, and these are the two subsequent values found. And here the total cost is 1.34. And looking back up here, that basically corresponds to the same solution found the second time I ran the integrated procedure. And then if I look up previously, the other optimal solution found with the integrated procedure actually had a lower total cost. So this first time I used it, I didn't find the best total solution. So in this case, what I can do is just re-execute all of this. And notice I've separated in different cells. So this is creating all the initial data. And then I've created a second cell and I called it run, because I can execute it multiple times. And every time I call randex, I'll get a different initial starting location. So if I call it a second time, I did get that second solution, which has the lower total cost. We can also use MATLAB's built-in ALA procedure. And what I'm going to do here is set the same random number seed as I used up here and run it. And you can see I do get the same result using the built-in ALA procedure. And I'm calling it, then if I want to control the random starting point, I'm calling it because the first argument of the ALA procedure is the random starting point. Okay. The second example of the ALA procedure, alternate location allocation procedure, is more realistic. And here I'm going to be looking at a two-dimensional location problem. So if I wanted to actually plot this, I basically have a total of 4 dimensions representing the location of, if I'm locating, say, 2 new facilities, that would be a 4-dimensional problem plus 1 dimension for the total cost. So I'd have to plot in 5 dimensions. So I can't plot anything in terms of a 2-dimensional location problem. I just don't have enough dimensions. So that's why we did the one-dimensional example, so that you could visualize a little bit what the actual optimization problem was. So for this problem, I'm going to use the US City 10K of set of data. So that's one that's already restricted to cities just with 10,000. I'm going to assign that to my P&W, use M as the size, N equal 2. And the W in this case is going to represent the population of these cities. So I'm going to use that as my monetary weight for this location problem. So I have a total of 134 cities. And when I plot that, this is North Carolina, South Carolina. These represent all of the cities of at least 10,000 population. And then to solve the ALA problem for an initial set of locations, I'm going to use the same set of locations defined by setting the random number seed to this value. And here what I'm going to do is I'm pausing the plot long enough so you can see what's happening. So the first random one was actually off in the Atlantic Ocean. And then every time it's solving a different iteration, the blue lines represent what the current allocation is, and it's alternating between locating and allocating. And for this particular problem, it's still continuing. And you can see the total cost reported in the command window keeps decreasing. And it did a total of 7 iterations and ended up with a solution at these 2 points. To do a single run of the ALA procedure, and then I'm going to call the long lat to city to see what the actual city is. So that I basically turned off delaying the pause plot. That's why it works so quickly. The first time I executed pause plot, which is a matlog command, and set it equal to 2-second delay, and then I reset it to 0 delay. So in doing that, I was able to solve the problem. Here's my total cost. And then the 2 locations are Charlotte and Cary, North Carolina, which for the 2 states you'd probably think is at least a possibility. You might think some of the cities in South Carolina might be one of the 2 best cities, but those are basically ones that you would actually expect to show up as the 2 best locations to serve all of the cities in those 2 states. And then since the solution depends on the initial starting point, it's a good idea if you have the computational time to do it to look at multiple runs. So in this formulation here, I'm going to look at a total of 10 runs of the ALA procedure. And then if you think about it, I'm sort of nesting the runs because the ALA procedure itself is an alternating procedure that looks at, for a given starting point, a series of locations allocations. And then I'm taking all of that and I'm embedding that inside of another for loop. And the way you can see what ALA is, if you look up the actual code of it, this is when I looked at the code of the ALA procedure, what it actually is doing, and it has a loop procedure here. And then I'm taking that procedure, which is embedded in this ALA function, and putting it into another loop that allows me to look at multiple runs. So when I do that, looking at the 10 different runs, notice that I start off with total cost equal to infinity. And that's the same thing I did up here in the code. And that way I know the first time I run something, I'll get a solution that's less than infinity. So that's a way of ensuring that the first time I call it, I set my first total cost to whatever that value is, and then that becomes my target value that is then improved upon if a better solution is found. If not, then that's just returned as the best solution. So here I'm running a total of 10 times. And if I wanted to take that solution, again, I typically tend to get pretty much the same solution in doing that. If I went back and looked at the integrated formulation that we were using previously for the one-dimensional problem, in this case then, since n is equal to 2, we're looking at searching in 4-dimensional space. So if we call fmin search, that Nelder-Mead procedure is searching in 4-dimensional space. When we do that, we pretty much get the same solution. So I'm actually returning the TC2 value found from the multiple runs of ALA, and then TC3 is the value found with the integrated solution. So they pretty much found the same total cost value, I think the same 2 cities. To be able to compare what is then the difference, since they got the same total cost, what you typically want to do then is look at, well, since they both seem to be performing the same way, which is better in terms of computational effort? And again, for this problem, it's happening so quickly that it's not a real issue, but there are a lot of problems in logistics where the computational time might be hours or even days of computation. So looking at this is important for a lot of problems. And the way that it is done in MATLAB is to use the tick-tock set of functions. And what that does is it sets a start time. So as soon as I execute tick, then it looks at the absolute computation time, how long the processor is spending solving the problem, and keeps track of that until the tock is executed. So everything, all of these multiple calls of the fmin search procedure are all going to be then added up, and the span of time between tick and tock will then be reported to the command window. And I'm going to set the same seed. I'm going to here close all the figures, and then here I'm going to do the ALA procedure with the same tick and tock formulation. So when I do that, here I'm getting maximum number of functions evaluations are reached, and that's just a, it's not an error, it's just reporting that is the value. And the reason is that this fmin search procedure, searching even in that four-dimensional space, is already reaching a maximum number of function evaluations. But the value returned at that maximum is actually, close to the best solution, or actually equal to the same best solution found by the ALA procedure. And if we look at the actual elapsed time, the integrated is actually faster than the ALA procedure. So that just shows that the MATLAB itself is actually really efficient at searching, at least in four-dimensional space. And then instead of looking at just two new facilities, here I'm going to set n equal to 20. And notice that everything kind of carries over. I just have to change this n equal 20. I can pretty much use the same code. And then here, instead of doing 10, I'm going to look at only 5 iterations in solving it. And the n then is used here as a second argument in Randex, and that generates then 20 initial starting solutions. So in terms of the Nelder-Mead procedure that fmin search is using, the search space is going to be then 40-dimensional. It's going to be searching in a 40-dimensional search space, as opposed to the ALA procedure, which is just doing the location separate from allocation. It's only searching in 2-dimensional space 20 times. You can see it's taking a little bit of time. So it took the integrated 13 seconds. And now if we look at the second elapsed time reported, the 3.6 seconds, that is found with the ALA procedure. So in terms of ALA procedure, it basically did it quicker and found a better solution, because also the total cost is higher for the integrated solution. So in a sense, this example is really the illustration of why we use the ALA procedure and why we just don't do an integrated solution, which I think would be sort of the obvious thing. Just take the objective function and solve for whatever the problem is. So the reason that the effort is taken to actually separate this problem into an allocation and a location phase is that as we get into this higher dimensional search space, by separating everything, we get better results quicker. Another thing I would like to highlight is that in running this procedure, one of the problems we can potentially run into is situations where even if we're using the randx function, where we're looking for starting locations that are within the bounding rectangle, since we're not using, say, the convex cell, which would give us a tighter set of starting points, that bounding rectangle might include, quite a large portion of space that is not close to any of our existing facilities. Think of, North Carolina and South Carolina. Part of the bounding rectangle for those states would include quite a large expanse of the Atlantic Ocean. So since we pick random starting points, we could conceivably have a situation where we have one random starting point that is actually off the coast of the Atlantic, and not actually closer to any of the cities than maybe a second random point. Say we generated 2 random points, one was way out in the Atlantic and another was a little bit closer to shore in the Atlantic. Well, in that case, based on our initial allocation, all of the cities are going to be allocated to the closer random starting point off in the Atlantic, and the one that's further out in the Atlantic is not going to have anything allocated to that. So that's an example. And then in terms of the way the ALA procedure would work is the new location then would use all of the cities, and essentially that city that's further out in the Atlantic would basically just stay at that location and not participate. So in essence, we'd be locating just a single facility as opposed to two. So that's an example of an edge case. Edge case are things that can cause problems with your procedure, sort of special cases that need to be considered. So that's one special case that can occur in the ALA procedure. So what I'm going to do here is I basically just copied over the same functional solution of the ALA procedure. The only thing I did is, and again, this procedure doesn't check for that edge condition. So what I'm going to do here is just randomly generate my two starting points. And these are both, I think, within the region occupied by all the cities, so it wouldn't illustrate this. So to force the first one to be way out in the Atlantic, I'm going to set it at longitude, latitude 00, which is off the coast of Nigeria. So now I take this as my starting point, and now when I run it, I get this solution, and you can see here that the first one is pretty much stated 00, and I can see that. Again, this is a large data set, so I don't want to look at the actual W matrix, so I can instead use the SPY command, which is part of MATLAB. And what that does is it pops up a window. And if you look in this window, you can see all of the blue represents the weights, and everything is assigned to the second new facility. And the first one is entirely empty. So that first one is never used for all of the 134 cities. In the case of the ALA procedure, one advantage of using a function versus a function handle is that in the function handle case, in just the code example, I haven't really handled that edge case. And there's a lot of situations where one procedure might have several different edge cases that all need to be handled. And the advantage of then putting this into a function is that you're able to handle the edge cases, and also you can check for the input values to make sure they have the right dimensions if that's important for the problem. Again, none of that would occur using this approach. So this approach is good if you're working for yourself and just want to get a solution, and if you saw that edge case, you would kind of just pick a different set of starting points and not going to worry about it. So this is good for sort of one-off personal use. But if you're going to be using a function yourself repeatedly, or especially if other people are going to be using a function repeatedly, it's probably a better idea to use a function so that you can handle edge cases and do error checking. So in the case of the ALA procedure, what the procedure does is it first detects an unallocated new facility by looking for the W matrix, and if it sees all the zeros, that just means that none of the existing facilities have been allocated to that new facility. And if it sees that, then what it does is it just randomly picks one of the existing facilities and then makes the new facility allocated to just that one existing facility, and then takes the previous allocation to one of the other new facilities and eliminates it. So essentially looking at, randomly picking one column of the W matrix, it takes wherever the W weight was previously assigned and assigns it to the unallocated location. Again, a simple little way, but it basically then for subsequent location allocation steps, that new facility that previously was unallocated is allocated to that one existing facility, but then when the second allocation occurs, it is also then typically close to a lot of other existing facilities. So at that point, it then participates in the rest of the procedure. So we can see that when we call the ALA procedure, and here I'm going to look at the SPY a second time, and when I do that, you can see that there's blue now in both rows of this procedure. So in both rows, it's actually doing the allocation. So this is what I would expect to see. And then secondly, if I look at the total cost, here it's 3.2 to the 8th, whereas previously with the previous solution, the cost was 5 to the 8th. So I get a lower cost solution because now I have two new facilities. Another example of the use of the ALA procedure is illustrated by the table that has the best retail warehouse locations in the United States. And we can basically duplicate that data, not exactly, but very close to what is actually reported in the table, by essentially solving a series of ALA procedures, because that's really what the table is reporting. So it starts with what is the single best location for a single distribution center serving retail, and then looks at 2, 3, 4, and so on. So in doing that, it's important that we're dealing with retail warehouse locations, and the reason for that is, and then in terms of representing the weight, we can use population as representative retail demand. If it was, say, warehouses used for some intermediate supplier, then that probably has no relation to actual retail demand. So using population would not be appropriate. Instead, you'd want to use weights corresponding to demand for that product across the country. That type of data is typically hard to get unless you have some special insight into that particular industry. So dealing with retail is particularly easy using this public data that we have as part of MATLog. So for this example, I'm going to be using the 3-digit zip data, and I'm going to look at just the continental United States. So I'll be using the multiple OR function, and I'm going to be looking at populations that are greater than 0. I think in the case of 3-digit zips, all of the populations are greater than 0. But the reason I do that typically is that for 5-digit zip codes, there are actually some 5-digit zip codes that have populations of 0. And I don't want to include those because they're not giving me any useful information. You might think, well, what 5-digit zip codes would have 0 population? One example of that doesn't really exist anymore was the World Trade Center. The World Trade Center was a large enough entity that it had its own zip code, but I don't think it had any condominiums or apartments, so nobody actually lived in the World Trade Center. So they had 0 population, but it had a 5-digit zip code. And there's actually lots of those entities throughout the United States. So if we were dealing with 5-digit zips, it's probably always a good idea to look for only those zips that have a positive population. So that's why I typically do that as a matter of course. Here I'm creating my data, setting the seed, and assigning the names of the cities and the states to 2 different variables. And I'm going to first solve the single facility location problem. And I can call that, and this is another example of not really an edge case, but a special circumstance where if I'm call the ALA procedure just with a single point, then it's essentially just solving the mini-sum location problem. And there's no real allocation required. So I get the solution. I'm going to call the long lat to city. And here I see I'm 43 miles from Evansville, Indiana. And in the table, the single best location was in Bloomington, Indiana. So to see how close Evansville, Indiana is from Bloomington, and again, I'm not that familiar. I think Evansville is sort of in the southern southwest portion of Indiana, but I'm not quite sure. So if I use the US city data to find Bloomington, Indiana, and then look at what I call delta here is the distance from the solution I found to the Bloomington, Indiana location, and basically I'm within 60 miles. So given the entire continental United States, that's pretty close to the same solution. Okay, the next thing I'd like to do to be able to duplicate the table is the table itself included travel time for that number of distribution centers. So essentially what it was doing was, in addition to getting the locations, was giving us some objective function value. And instead of giving what the raw function value would be, since we're using population as our monetary weight, we'd be essentially looking at people miles. So we'd have some billions or trillions of people miles, and that probably doesn't make any sense. So to make it into a number that makes more sense, we can take the location of the different 3-digit zips from the allocated distribution center, and then using the population allocated as a weighing factor, we can determine what is a weighted distance from that distribution center to all of the 3-digit zips allocated to that distribution center. So that gives us then an average distance, and then to take that average distance and convert it into time, we can use the fact that a truck can travel on average about 400 miles per day. So we can take that distance and 400 miles, and we're also going to be wanting to use at least an estimate of the actual road distance. So this is our first parameter, the distance per day traveled by a truck. And then second, we're going to use a circuity factor of 1.2. And then with that, we can calculate the distances by just multiplying the great circle distances by the distance per day to get that value. And when we do that, we get an average distance of 846 miles. So essentially this is saying from Evansville, Indiana, the average distance, population weighted to everybody in the continental United States, is about 846 miles. And then if we look at a demand-weighted average distance, then a demand-weighted average distance is actually a little bit further, 942 miles. So looking at the raw mean of the distance gave us a lesser value. I think an explanation for that is that Evansville, Indiana is in the middle of the country. A lot of the population center for the United States is up in the Northeast. And since when we do the population weighing, then the average distance gets a little bit further, since more of the population is further away, as opposed to just the 3-digit zips. Another way of saying it is that the 3-digit zips in the northeastern portion of the United States, each of those have larger populations than the 3-digit zips in the central part of the United States. And then we can combine all of this, then take that demand-weighted average distance and then divide it by the distance per day traveled by a truck and get 2.35 miles as our estimate of what is the average distance traveled. And comparing, the table itself had 2.2. So again, we're close to the value reported in the table. Next, looking at locating two distribution centers. In the table, the two locations were Ashland, Kentucky and Palmsdale, California. And we can run the ALA procedure. I'm going to do a total of 5 runs for n equal 2 and see what the result is. And when I do that, I end up with Lexington, Fayette, Kentucky, and then Portersville, California. And to see how far those are away, first I'm going to calculate the longitude latitude of the two locations from the table. That I can calculate the delta, and the first value then says that the value of Lexington is 40 miles from Ashland, and the value of Portersville is 105 miles from the Palmsdale solution reported in the table. So again, this solution is tracking the results in the table. Obviously the data is probably slightly different, but it's basically the same approach. So then for general n, we can, in this case, say let n equal 8. I end up with this set of 8 locations. The next example I would like to talk about is demand point aggregation. And for this example, I'm going to first look at the centroid solution. So what I'm going to first calculate is a function handle that gives me the one-dimensional centroid. And the reason is I'm going to be using the same set of data for I-40 that I used previously. So I'm going to redefine those P points to be the mile markers of the 7 cities. M is equal to 7. I'm going to set W again equal to just the M maximum 1 through M values, again just as a way of illustration. So in terms of the optimal centroid location, xcog, I get 280.71. And if I wanted to compare that to using the mini-sum location solution, when I solve that, I get the median location of 270, which corresponds to, I think, Durham as the optimal city location. Notice that the centroid is not at a city location. To be able to demonstrate that the centroid is indeed the optimal location, then what I'm doing first is using the 0 mile marker just for convenience without loss of generality. I could pick any other arbitrary point, but from this arbitrary point, what I would like to do is have my total cost be the same using the aggregate point versus if I looked at what is my total cost for all of the 7 existing cities in terms of weighted distance. So I can get that by just here taking the dot product, and I get a total cost value of 7860. And if I then compare that to using just the single centroid point and multiplying that then times the sum of the weights, I get the same 7860. If instead I'd use the median location in Durham, I would end up with a value less than that. So it shows it's not the same problem. So using the median location as my aggregation point, I would actually end up with a different problem. I wouldn't really be matching the weighted distance problem. In the case of using something other than just distance, if I use, say, square distance, then I can redefine my location as being the square root of the weights times the square of the distance. In this case, the distance is just the x coordinate. So I can just square the x coordinate, and then all of that divided by the sum of the w's, and then the square root of all of that. So that becomes my function handle. And looking at all 7 cities, the objective function value here is 2.47 million. And those are units of square miles times the W value. So the units don't really make any sense. But if I went and then used my centroid value and then squared that times the sum of the weights, I would end up with a different value than the 2.47. If instead I looked at the square of the distance reported using this method of calculating, the square root method of calculating, then I actually get the same value. Here it looks different, and the reason is there's a little bit of numerical error. One way of kind of seeing the underlying value is to call m distance, and here you can see it is the same 2.47. And then the last example is an example of, say, instead of using the 3-digit zip, which is a little under 1,000 for the continental United States, if I wanted an even smaller data set, say a lesser number of points, I could create one by using the 3-digit zip data and use it to create 2-digit zip data. And the thing I want to do then is take the population that of 3-digit zips that comprise that have the same first 2 digits and add all of that up as the population, do the same for the area, and then for the location I can calculate the centroid and use that as my new location for that 2-digit zip. And first thing I'm going to do is calculate a function handle that gives me a 2-dimensional center of gravity. And so I'm going to give it in this case, a vector of 2-column vector of xy coordinates and a vector w of weights. Here I'm not going to assume any orientation for the weights, so I'm forcing it to be a row vector and then multiplying that times the first column of x. Here I'm multiplying times the second column of xy, and all of that then is going to be divided by the sum of w. So this defines the center of gravity. It's probably a good idea to use a function handle in this case. I could basically, when I want to do the calculation, just put all of this code here, but I'd have a hard time if I looked at this. To me, it wouldn't be obviously clear that that's the center of gravity calculation. I mean, I could put some comment over here saying this is the center of gravity, but I think it does just as well to actually just label a function handle, and that way I can use it multiple times in my code and have that information. Again, there's a fine line between putting the details in the code versus a function handle versus at the other extreme creating a function. Again, the advantage of a function might be edge conditions and error checking. So this is sort of in that middle ground where I'm using the function handle to collapse a little bit complicated calculation, at least visually, to see what's happening. And then when I use it, it's really clear what the intent of using it. So later on in the code where I'm calling xy cog, it's clear that I'm calculating the centroid for this set of values. And here the function, when I call it down here, what's more interesting is what are the two arguments? What are my XY values and what am I using as my weights? In this case, I'm using the population as my weights. And here I'm using the zip code, longitude, latitude as my XY points. So first I'm going to assign to Z my 3-digit zip data. And I can just look at Z. This is all the data. There's 913 points. And then to take the 3-digit code data. So if I looked at a 3-digit code, let me just take an arbitrary piece of data. I'm going to look at code 3. Let me just take 100. So its code value is 115, and it's actually 3 digits. So converting this to a 2-digit, the first two digits are 11. So what I can do is take this value, divide it by 10, and now I get 11.5, and then take all of that, and then just take the floor of that, and I get 11. So that's the idea here. I can do it to the entire vector of code 3 values, and I'm going to reassign it to a new field of Z called code 2. So when I do that, now if I look at Z, I have a code 3, which is with the original data, and I've added a new field, code 2, which is the code that I want to work on. And if I look at the number of values, again, I have 913 because all of the 913 3-digit zips have, the first 2 digits reported in this field value. But what I really want to do then is reduce that to what are just the unique sets of 2-digit codes. And there's a function in MATLAB called unique, and I could just give it that vector from the Z structure, and it'll actually create a new vector. In this case, it's 99 elements. So there's 99 values that have unique first 2 digits, which is what you would expect going from 0 to 100. But it could be cases like in the case of going from 5-digit to 3-digit, there are actually some 3 digits that don't appear. Looking at here, for example, the 913, that's not equal to 999, which would hold true if the going from 3 to 2 rule applied. So there's some 3 digits that don't appear in any 5-digit codes. So that's why using the unique is important, because you're not spending time or adding erroneous data. So unique allows us to focus on just the unique elements found corresponding to unique first 2 digits of 3-digit codes. So with that, then, now that I have a vector, I can then just set up a for loop and then loop through each of the 99 unique 2-digit codes, and then I can use the US 3-digit data, and then I'm going to assign using the multiple OR command, I'm going to basically look then at all of the same 2-digit codes. So I'm looking at the particular value I of the first 2 digits I'm looking at, and then I'm looking at for all of the other 2-digit codes, which ones have the same value, and return all of those into a structure. So when I do this, I'm going to first set Z equal 1, and when I do this the first time, I'm not going to do the semicolon so you can see the results. I basically found 4 elements. So I can then execute this for loop and basically give it these 3 names. So it'll store that in a .mat file. And then one nice thing about that is I can go, and if I want to go ahead and clear all the variables out of my workspace, and then if I do load, give it the name US zip2, I just have those 3 pieces of data. So it's a nice way. And then all of the XYs represent the centroids of the underlying 3-digit zip code areas. And then the areas represent the sum of the areas and the sum of the populations. Again, that's done with these 2 sum calls, and here with the center of gravity or centroid call. And then the last thing is to do a plot of all the locations. And here, notice that there's, I think, 1 in Alaska, which is right over here, 1 in Hawaii, and 1 2-digit over in Puerto Rico. So all 3 of those locations have unique 2 digits. And here, if I zoom in a little bit, it looks like there's I think probably only maybe one or two North Carolina 2-digit zips. And it's a much sparser set of data compared to the 3-digit zip data.